On May 29, 1919, astronomers on two islands off the coast of Africa pointed cameras at a total solar eclipse and measured starlight bending around the sun by close to 1.75 arcseconds. The number, a strange new theory predicted, and roughly double what 3 centuries of Newtonian physics said it should be. In September of 2015, 2 L-shaped detectors in Louisiana and Washington state picked up a signal a fifth of a second long, a stretch and squeeze in the fabric of space itself, caused by 2 black holes colliding over 1 billion years ago, arriving so faint that at its most sensitive, that instrument can register a change in its 4-kilometer arms 1/10,000th the width of a single proton. In April of 2019, we published an actual photograph of a black hole's edge, an orange ring around a dark center 55 million light-years away at the heart of the galaxy Meters 87. 3 separate confirmations, a century apart, that gravity is not a force reaching out and pulling objects toward each other. It's the shape of space and time themselves, bent by mass and energy, exactly the way one set of equations from 1915 said it would be. And after 100 years of getting every decimal point right, we still cannot tell you what gravity actually is. Not what it does, what it is. That gap between predicting gravity perfectly and understanding it at all is where this video lives. And I want to start by naming the specific wrong idea that most people who actually follow physics carry around in their heads. Because it's not a dumb idea. It's a reasonable one. It's just probably backwards. Here's the idea. Physics has 4 fundamental forces: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. Over the 20th century, physicists figured out that the first 3 are all, underneath everything, about particles. Electromagnetism is 2 charged particles trading photons back and forth. The strong force is quarks trading gluons. The weak force is particles trading W and Z bosons. This is the standard model, and it is the most thoroughly tested framework in the history of science. So the obvious next move, the move that feels less like a hypothesis and more like finishing a sentence someone else already started, is to assume gravity works the same way. Somewhere out there is a particle, the graviton, that 2 masses trade back and forth to produce what we experience as gravitational attraction. Find the graviton, slot it into the standard model, and physics is essentially done. That's the belief. It's not fringe. It's the default setting in the head of anyone who paid attention in a physics class. And for nearly a century, some extremely serious people have been trying to make it true. Here is the specific place where it breaks. When physicists take the mathematical machinery that successfully quantized electromagnetism, the procedure that gave us the photon, and point that exact same machinery at gravity, the equations don't behave. They produce infinities. Not the ordinary infinities that show up in electromagnetism too and get canceled out through a technique called renormalization. Those are manageable, almost routine. Gravity produces an endless cascade of new infinities at every order of approximation. ones that never stop appearing, no matter how many correction terms you add, and they refuse to cancel. Physicists have a word for a theory that does this: non-renormalizable. It's not a rounding error, it's the equations themselves telling you that the starting assumption. Treat gravity like the other three forces, just harder. Might be the wrong starting assumption entirely. Something Jacob Bekenstein stumbled into in 1972 while he was still a graduate student at Princeton is where the alternative starts. And it starts, of all places, with a cup of tea. Bekenstein's advisor, John Wheeler, posed him a problem that sounds almost like a joke. Take a hot cup of tea, full of entropy, full of disorder, full of information about the exact motion of every molecule in it, and drop it into a black hole. The tea crosses the horizon. It's gone. As far as anyone outside can ever tell, that information has vanished from the universe. But physics has a law, the second law of thermodynamics, that says the total entropy of a closed system can never decrease. So where did the tea's entropy go? Either the black hole itself carries entropy, meaning black holes aren't the featureless, information-free objects everyone assumed, or the second law of thermodynamics, one of the most reliable statements in all of science, is simply false the moment a black hole is involved. Bekenstein took the first option seriously and worked out that a black hole's entropy has to be proportional to something specific, not its mass, not its volume, but the surface area of its event horizon. Stephen Hawking initially thought this was close to nonsense and set out to prove Bekenstein wrong. Instead, in 1974, Hawking discovered that black holes aren't perfectly black at all. They emit a faint thermal radiation, now called Hawking radiation. And that discovery handed Bekenstein's idea an exact number. A black hole's entropy equals exactly 1/4 of its horizon's area, measured in a unit called the Planck area, roughly 10 to the minus 70 square meters. Work that formula for a black hole the mass of our Sun, and you get an entropy of roughly 10 to the 77th. A genuinely staggering amount of information, capped not by how much three-dimensional space is inside the black hole, but purely by the two-dimensional area of its boundary. Sit with that for a second, because it's the strangest sentence in this entire script, and it's also completely mainstream, accepted physics. The maximum amount of information you can pack into any region of space isn't set by its volume. It's set by the area of the surface enclosing it. Every other object you've ever encountered, a bookshelf, a hard drive, a brain, has an information capacity that scales with volume because you can keep adding more stuff inside. Black holes don't work that way. And in 1993, the physicist Gerardus Hooft, followed shortly after by Leonard Susskind, asked the question that idea was begging for. What if that's not a weird black hole exception, but a clue about the actual architecture of reality? What if everything that happens inside any volume of space can, in principle, be fully described by information living on that volume's boundary, one dimension down, the way a hologram encodes a three-dimensional image on a flat two-dimensional surface? They called it the holographic principle, and for years it was an elegant guess without proof. The proof, or the closest thing to one, arrived in November of 1997 from a young Argentine physicist named Juan Maldacena. Maldacena's paper is called The Large N Limit of Superconformal Field Theories and Supergravity, and it is, as of today, the single most cited paper in the history of theoretical physics, more than 20,000 citations. What he showed was a specific mathematical equivalence, a full theory of gravity operating inside a five-dimensional curved space called anti-de Sitter space produces the exact same physics, every calculation, every prediction, as a completely different theory, one with no gravity in it at all, living on the four-dimensional boundary of that space. Not similar physics. The same physics in two different mathematical languages, one dimension apart. It's called the ADS/CFT correspondence, and in the years since, it's become one of the most productive tools in all of theoretical physics. Condensed matter physicists now use it to study superconductors. Nuclear physicists use it to study the quark-gluon plasma left over from the Big Bang. But the part that matters here is what it implies about gravity itself. In that mathematical universe, gravity isn't one of the fundamental ingredients of reality. It's a shadow, a description of what a completely different, gravity-free theory looks like when you view it from one dimension up. It has never been mathematically proven that our actual universe, which isn't anti-de Sitter space and doesn't obviously have this exact boundary structure, works the same way. That's the honest caveat, and I'll come back to it. But it opened a door that a physicist named Ted Jacobson walked straight through 2 years earlier, in 1995, using nothing but Bekenstein's teacup. Jacobson's paper asked a very specific, very testable question. If you assume, the way Bekenstein and Hawking's work implied, that entropy is proportional to the area of any local horizon, not just black hole horizons, but the horizon any accelerating observer would perceive at any point in space-time, and you combine that with the most basic equation connecting heat, temperature, and entropy and all of thermodynamics, what do you get? He worked through the derivation, and what came out the other end was Einstein's field equations, the actual equations of general relativity, the ones that predicted the 1919 eclipse deflection, that predicted gravitational waves, that predicted the shape of the shadow in that 2019 black hole photograph, fell directly out of a thermodynamic argument, with no assumption anywhere that gravity itself was a fundamental force being plugged in. Jacobson's own conclusion, at the end of that paper, was that trying to directly quantize the Einstein equations, trying to find their graviton, might make about as much sense as trying to quantize the wave equation that describes sound moving through air. Nobody looks for a fundamental sound particle. You quantize the atoms of the air, and sound is simply what emerges, statistically, from trillions of atoms bumping into each other. It's real. It has a wave equation you can write down precisely. It is not, itself, one of the basic ingredients of the universe. That reframes the entire graviton hunt. It isn't failing because our instruments aren't sensitive enough. A detector that can register 1/10,000th the width of a proton is not the bottleneck. It might be failing the way a hunt for the heat particle would have failed a physicist in 1750, before anyone understood that temperature isn't a substance at all, just the statistical average of how fast a huge number of particles are jiggling. Gravity, in this picture, might be the sound. The atoms, whatever the actual fundamental building blocks of space and time turn out to be, are the thing nobody has found yet. And the graviton was never going to be the right place to look for them. For the same reason, there's no such thing as a lone heat particle to isolate in a magnetic trap. In 2010, the physicist Eric Verlinde pushed this from a mathematical curiosity toward a concrete physical hypothesis. He proposed that gravity, ordinary Newtonian gravity, the force that keeps your coffee cup on the table, is what physicists call an entropic force. Not a fundamental push or pull, but the macroscopic result of a system statistically favoring more probable, higher entropy configurations. The classic textbook example of an entropic force is a stretched rubber band pulling back toward you. There's no fundamental rubber band force written into the laws of physics. The band's polymer chains simply have vastly more ways to arrange themselves when they're short and tangled than when they're stretched taut. And the pull you feel is nothing but that statistical preference expressing itself as a force. Verlinde derived Newton's law of gravitation, the same inverse square law that's been correct since 1687. Starting purely from Bekenstein's holographic entropy and nothing else. And in 2016, he extended the idea to something with real observational teeth. He proposed that on the scale of entire galaxies, this same entropic effect could account for the extra, unexplained gravitational pull that astronomers have spent 50 years attributing to an invisible substance called dark matter, without needing a dark matter particle to exist at all. So, does it work? This is the part where I have to be honest with you about something that genuinely unsettles me, because it's the exact point where an elegant idea meets data. And data doesn't care how elegant an idea is. In 2016 and 2017, a team led by the astronomer Margot Brouwer used a technique called weak gravitational lensing, measuring how the light from over 33,000 distant galaxies gets subtly bent by the mass of 33,000 foreground galaxies sitting in front of them, to run the first real test of Verlinde's proposal, using no adjustable free parameters at all. And for isolated galaxies, it worked. Verlinde's formula, derived from pure thermodynamic reasoning with nothing tuned to fit the data afterward, matched the observed lensing signal about as well as the standard dark matter model does. That result was published in the monthly notices of the Royal Astronomical Society, one of the most respected journals in the field, and it is a genuinely startling thing for a 100-year-old alternative idea to pull off on a first try. But other teams pushed the same theory further out, to galaxy clusters, the largest gravitationally bound structures in the universe, using X-ray and lensing data from a separate survey called CLASH. And there, the standard dark matter halo model fit the full sample of clusters well, while Verlinde's emergent gravity reproduced only a handful of them accurately. The theory that looked beautiful on the scale of a single galaxy started fraying at the scale of a cluster of galaxies. I want to be straight with you about what that means, because science communication has a bad habit of either declaring every new idea a revolution or dismissing every unresolved idea as fringe, and neither of those is honest. This is not a debunked theory. It's not confirmed physics either. It is a real, published, peer-reviewed hypothesis that has one genuine observational success and one genuine observational strain on two different length scales, and as of right now, nobody has a single version of it that handles both consistently. I find that uncomfortable to say out loud, because the thermodynamic argument underneath it, Bekenstein's entropy, Jacobson's derivation, the whole chain of reasoning is, to me, one of the most persuasive things in modern theoretical physics. I want the elegant answer to be the true one. But wanting an answer to be true has never once made it true, and the honest state of this research program, right now, in 2026, is unresolved. That's not a failure of the idea. Genuinely replacing an assumption that stood since 1687 was never going to be tidy on the first attempt. But it's also not something you get to skip past on the way to a clean, triumphant conclusion. And I'd rather tell you that plainly than pretend this is more settled than it is. Here's where the floor drops out from under the original question. If gravity really is emergent, a statistical, thermodynamic consequence of something more fundamental, the way temperature emerges from atoms and sound emerges from air, then the thing gravity is a description of the shape of, namely space and time themselves, might not be a basic ingredient of reality either. They might be exactly the kind of thing physics eventually learns to see through, the way the 18th century eventually saw through heat as a substance and found atoms underneath. In the years since Maldaceno's paper, physicists, including Mark von Ramsdonk, have pushed this idea further, arguing that the geometric connections of space-time, the very fact that one point in space is near another point, can be built directly out of quantum entanglement between the more fundamental, non-geometric degrees of freedom on the boundary theory. Cut the entanglement in the math, and the space-time on the other side of the correspondence literally tears apart. Maldacena and Susskind went on to propose, in 2013, a conjecture they called equals Epper, linking the wormholes that Einstein and Rosen described in 1935 to the entangled particle pairs that Einstein, Podolsky, and Rosen described that same year, suggesting those might be the same phenomenon viewed two different ways. None of this is proven. All of it is active, contested, genuinely open research, argued about at conferences right now by people who disagree with each other. But the direction it's all pointing is the same direction Bekenstein's teacup pointed in 1972, that the stage every other law of physics performs on, space, time, distance itself, might not be the floor of reality. It might be one level up from the floor. Which brings us back to where this started, and to the thing I actually want you to walk away from this video believing. The idea that a graviton is out there waiting to be found, that gravity is simply the fourth force, still owed its particle, still owed its slot in the standard model, isn't a stupid idea. It's the most natural extrapolation anyone could make from 3 genuine, spectacular successes. But every piece of evidence in this video, from a cup of tea in 1972 to a weak lensing survey in 2016, points toward the possibility that the extrapolation itself was the mistake. That gravity was never a force waiting for its particle, any more than temperature was ever a fluid waiting for its atom, or sound was ever a substance waiting for its molecule. We didn't fail to find the graviton because we haven't looked hard enough. We may not have found it because there was never a particle there to find. Because gravity was never the fundamental thing to begin with. It was always the shadow. And if space and time turn out to be the screen that shadow is falling on, rather than the wall behind it, then the ground you're sitting on right now, the seconds ticking past as you watch this, were never the floor of reality to begin with. They were already one level up.